And I am greatly honored and delighted to have been asked to present a Whitehead lecture on the occasion of this double celebration, a double anniversary, if you like. I realize that, as they say in showbiz, Whitehead is a very hard act to follow. But also, as I was listening to the previous speakers in their formal recounting of what went on here and their informal recounting of what went on here, so many stories occurred to me that are parallel. The world of mathematics is not that large, so that one does not connect in some way, even when one is an outsider, with some of the things that I heard just a few minutes ago. I think that all mathematicians sitting here, maybe all mathematicians quite generally, are beneficiaries of Whitehead's legacy. The deep formalization of mathematical logic that occurs in Whitehead and Russell, even though it failed in its original intent of providing an incontrovertible basis for the truth of mathematics, for the certitude of mathematics, has been tremendously fruitful in adding significant chapters to our understanding of mathematics and, let us say, even of computer science. And then we have Whitehead's message for education in the book The Aims of Education, which was alluded to earlier, the message being that one ought to teach things that are relevant to the current generation. And I think that this is still an important point, which is sometimes forgotten. And then as far as this formal philosophy is concerned, which is very difficult, this process philosophy, what I should say is that it simply reminds us of the provisional nature of our most substantial accomplishments and of our deepest thoughts. Much more personally, and I think this is going to be quite a personal lecture, I have admired Whitehead, also Russell, but these are two different personalities, really. I wonder often how they ever got on with one another. But I admired Whitehead because in his lifetime, I think he had something like 4 or 5 different careers. Mathematician, logician, administrator, educational theorist, metaphysician, philosopher, all of these things. And to some extent, I've tried to use him as a role model. I don't know how successfully, but I've always had him in the back of my mind. As an undergraduate, I studied the Principia, not in its original form, but in a form that was modified by one of his principal followers, W.V.O. Quine. I had courses essentially in Principia with Quine's version of it. Now, Whitehead came to Harvard from Imperial the year after I was born. And he retired, I think for the second time or for the third time in his career from Harvard the year before I matriculated. So I never had the opportunity to have a course with Whitehead, but I used to see him puttering around Harvard Yard, and everybody knew this was Whitehead. And he would walk around and so on and so on. Yes, this is Whitehead. And then I remember very vividly, I would walk home a young lady whom I married not shortly afterwards, and still am married to. Remarkable these days. And we used to pass a certain block of flats. And I used to say to her, to my wife, and she would say to me, "This is where Whitehead lives." And we would sort of walk silently and kind of bow our heads a little bit. This is the house in which Whitehead lives. But I never knew him, never had a course with him. I have to start off with an excuse. I am not really a philosopher, perhaps a Sunday philosopher, the way that Winston Churchill was a Sunday painter. I think, in my experience, most working mathematicians don't like philosophy. They hate it. And yet, unconsciously, there is a philosophy to which they subscribe. It is, generally speaking, the philosophy of Platonism, or the philosophy of formalism, or a mixture of these two. And early on, I saw that the program of the Principia Mathematica was far more Platonist than I liked. And as generally happens with children, children rebel against their parents and against their teachers. They have to, otherwise there'd be no progress in the world. And so I very soon afterwards rebelled against the strictly Platonist interpretation and the thought that one can make mathematics incontrovertible. Now, forget what the title of this lecture is, Mathematical Evidence, and there are several ways, several interpretations you can give to these two words. One is becoming much more prominent. That is the role of mathematics, particularly mathematical statistics, in the law. For example, in DNA testing, or in big controversy in the States on how do you count the population? Do you count noses or do you allow sampling? And this has reached the courts. So it's now a federal case in federal court on what one is allowed to do. So this is mathematics in the service of, might say, legal practice, and it's a thought that goes back at least as far as Leibniz. But this is not what I want to talk about. I don't want to talk about this, although I do know something about it. I want to talk about evidence within mathematics itself. Now, I would think that for 100 years at least, the philosophy of mathematics has limited itself to one topic, not exclusively, but almost perhaps 90%. And that topic is foundations. What are meant by foundations? Well, I like to say that the foundations of mathematics concern themselves essentially with one question. Why is mathematics true? Now, there's been so much written on this point, on this subject, that I think the philosophy of this question is largely played out. And I and some colleagues who are sympathetic to my point of view have tried to move the philosophy of mathematics away from this question into other questions. There are other questions that are equally interesting. For example, the question of why is mathematics useful? Or when is mathematics counter-useful or deleterious? And I'm talking in the social sense. But anyway, despite my efforts and efforts of sympathetic colleagues, the first question of why mathematics is true, it's like the phoenix. It dies and it rises. It dies and it rises. You can't put it down. Everybody wants to discuss it. And so, since one of Whitehead's contributions, perhaps his main one, I'm not certain, I wouldn't want to give value points to these things, is the Principia with Russell. I thought that I would give you my own take on this question, but I want to change the question. I want to change it to this, not why is mathematics true, but why do I, Phil Davis, believe or give credence to the statements of mathematics that I deal with? Why do I believe in them? What's my commitment to these statements? And then, as I do this, I ask you, I invite you either now or later in leisure, to take some of the things that I talk about and ask yourself the same question. Why do you believe that the things that you're dealing with are true? Now, as I say, I'm going to approach the question from my personal background of research and applications, university teaching, and I'm not here particularly to create a system. I'm not strong enough in philosophical technique to create a system, but put forth some ideas that you might find stimulating. Now, the concept of belief is itself inextricably related to a multiplicity of philosophical concepts that have been discussed ever since the pre-Socratics, I'm sure. Belief, being convinced, truth, knowledge, understanding, reason, logic, meaning, explanation, existence, all the different components of epistemology and ontology, all of these play a role. But I'm going to leave these high-flown things. I don't want to pile abstraction on abstraction and metaphysical concept upon metaphysical concept. I'm going to be quite down to earth. I suppose that many professional mathematicians might answer my question of mathematical belief by saying, and this is their credo, I believe because it has been proved. I believe that it has been because it has been proved. Short, simple, sweet. In fact, I heard not so many months ago, I heard one graduate student telling another graduate student, in mathematics, the name of the game is proof. That's the name of the game, proof. Not with me. With me, my belief is not so simple, not so sweet, and perhaps not so short either. Now, let me tell you how I'm going to proceed. I'm going to take some simple statements that you've heard. Very simple. I'll start with really at the bottom, 4 years old maybe. I'll build it up a little bit, not too much. And I'll give you, for each one of these statements that I make, some comments which refer to why I happen to believe them. And then you might do the same as I suggest for yourself. Then, after I do that, and I'll perhaps go through 10 of these, depends on how my time is. After that, I'll try to abstract just a little bit and talk about different components, make a taxonomy, you might say, of belief, of reasons that contribute to, that I have found, contribute to my belief in such statements. So let's start. Let's start with, I believe that 2 plus 2 equals 4. Well, I had 2 groups of 2 oranges apiece, and I started to count them, and the counting stopped at 4. So I believe it. And then I was told by my father when I was quite young that 2 and 2 is 4. And what he said was so. And then we used to have a little copybook in grade school, and on the back there was a little table there. There were 2 tables, in fact. One was for addition and one was for multiplication. And it said in my addition table, 2 and 2 is 4. In the course that I took with Quine, and this occurs in Russell and Whitehead, we got up as far as 1 plus 1 equals 2. This was a la Whitehead Russell after, I don't know, 300 pages or something, something like this. So this has added to my belief, multiplying both sides of the equation by 2. that 2 plus 2 is 4. You see, so I have here, I've given you 3 or 4 different reasons why I believe that. But let me complexify things a little bit. 2 and 2 is 4, and 7 is 14, but 7 and 7 is also 2 in clock arithmetic. So 7 and 7 is 2, and this points out the fact that what 2 and 2, or 7 and 7 is context sensitive. Depends on the context. You have to specify a context. And I wonder how you can thoroughly specify a context. In order to specify a context, you have to go outside of mathematics itself. You have to go out into meta-mathematics. You even have to go into the common language. This is one of the points that Leavis made against C.P. Snow in the classical argument on two cultures 30, 40 years ago. You have to discuss what the comprehensibility of symbols means, or just where it resides, and so on. All right, that's the first instance. Let's make that a little more complicated. I believe that 4519 multiplied by 8203 is 37,069,357. I believe this is well, I wouldn't say that I believe it as firmly as I believe that 2 and 2 is 4. Now, I have not counted. I didn't do any counting to get that. I worked it out with an algorithm that was taught to me somewhere in grade school, long multiplication it was called. I also asked my wife to work it out. She worked it out and got the same answer. Well, that's some evidence. There's some evidence that my answer that I gave is correct. I checked out my answer using certain tests. I had learned about casting out nines. I don't know if it's taught anymore. I cast out the nines. And I know that this is a necessary but not a sufficient condition for the truth of a multiplication. But it was a little bit of evidence when I got the nines residue the same on both sides of the equation. Yes. And then I took the little handheld computer that I got free from a bank when I opened up they gave me one when I opened up a new credit card. Little one, and it went up, and it gave me the same number. So another piece of evidence. I have not proved my answer back from basic assumptions, using either Whitehead and Russell's idea or using Peano maybe. No, I didn't do that, and I wonder whether the manufacturers of cheap computers and so on, I wondered whether they had checked every possible combination, or whether that particular one they had gimmicked up in some way. And if they had checked it, who checked the checkers? And so on. I mean, this is infinite regress. Let me move on from that problem in multiplication. I believe that the Pythagorean theorem for a right-angled triangle in 2-space is true. Euclidean geometry. Well, there's the context again in Euclidean geometry. I believe it's true. I took a ruler and I measured, and it was approximately true. Well, an approximation to something is a piece of evidence. I found that it was approximately true by measurement. And then in high school, I proved it. Well, it was in the book. I read the proof. Yeah, that convinced me. And then I learned that there were not only the proof that was given in my textbook, but there were hundreds of different proofs that people over the years had thought through. And some of them were very visual proofs. You could just see it. You didn't have to write down any symbols at all. Almost like the thing that Professor Heyman showed with the chessboard, a very visual sort of proof. That's a very strong piece of evidence, something that is visual. And then I was a little bit confused a little bit later when I got to calculus and learned about the arc length and the Pythagorean theorem for differential equations. And I learned that ds squared is dx squared plus dy squared, and they told me that's a definition, not a proof. Well, this kind of confused me a little bit. And then I learned a little bit later on, when I was a little more sophisticated, that there was a sort of a duality between where you started and where you finished, in a definition and a theorem. And a definition can lead to a theorem, but a theorem also might be taken as a definition. Another point. I learned sometime that a minus times a minus is a plus. By definition, maybe. A minus quantity is a manner of speaking. The truth of the matter is that any quantity, whether it's plus 6, 9, square root of whatever, quaternion, is a manner of speaking. It's convenient that a minus times a minus be a plus. Why is it convenient? Well, it extends, it unifies, it creates new formalisms which are new possibilities of inquiry. It's convenient. We have freedom. We can make our definitions. They're not all convenient, though. You can go out and make any definition you like, and most of them will die from lack of convenience. Case number 5, example number 5. I believe I cannot square the circle. I believe this. Well, let's say a little more sophisticated. I believe that pi is a transcendental number, and from which you would follow with some other stuff that you cannot square the circle. Why do I believe this? Well, when I was younger, I tried to square the circle. Many people do. I failed. And then I read that many people have tried over the years and failed. So this is an argument from what they call an argument from silence. Something doesn't work. But of course, many people have tried Fermat and failed. So what kind of an argument is that? But still, it's an argument. It's argument. There's evidence. I'm almost arguing here that we, as a group of mathematicians, constitute a court of law in which we weigh a variety of evidence. Well, then I read that the statement was proved. In this form, the transcendental form, fairly late. In the late 80s, of 1880, something like this. Fairly recently in the history of mathematics. I've not read the proof. I have eyeballed the proof. It involves some integrals. I said I could handle that. Yeah, I can handle that. It wasn't too long. It wasn't 5,000 pages. There was a few pages of integrals, but I never read the proof. I cannot reproduce it. I have no interest in reproducing it or devising my own. I don't know how many people here have read the proof that pi is transcendental, or how many people here accept that as a fact. But I accept it as a fact. This is evidence by authority. The authority it is the consensus of the mathematical community. But what do you do about the cranks in the world? Perhaps many people here have gotten letters from cranks, and they have given a two-line proof of Fermat and a proof of the squaring of the circle and the dimensions of the Great Pyramid and the pillars out there in Stonehenge and the connection to mathematics and so on. It's all wrapped up in one meta-theorem, and you get it in an envelope. What do you do with that? Is this a crank or is this a genius? How can you tell? Is there some necessary and sufficient condition which rapidly distinguishes a crank from a genius? We know that George Cantor was a crank, was a genius, both, wrapped up in the same brain. Well, anybody that goes public with mathematics gets letters like that, in which he summarily will throw the stuff into the trash basket. But maybe in the course of throwing out, he's throwing out something that is valuable. One never knows. I believe, number 6, I believe that there are infinity of twin primes. I've not proved it. I think no one has proved it. I think there's a lot of experimental evidence around that's so. I think that within a probabilistic interpretation of that theory and in number theory, that one might even consider a proof. It fits in nicely with a variety of experiences. Let me ask a question. Does the truth of a statement depend on somebody having proved it? Or is truth independent of proof? Or independent of evidence? Number 7. I believe that the derivative of x squared is 2x. I believe this. Well, I have a number of reasons for believing this. One is that I checked it out using the rule for x to the n power. I put in n equals 2. Checks. Then I checked it out approximately with a pencil and a piece of graph paper alluded to earlier as one of the inventions, modern inventions. I drew a parabola, y equals x squared, and looked at the tangent. And the tangent slope seemed approximately to be twice the abscissa. And then I checked it, went to my favorite computational package, MATLAB, and I checked it out numerically using difference quotients. Yeah, it's pretty good to 15 figures. Very good, very good. I know also historically that Newton knew that the derivative of x squared was 2x. And I knew that Leibniz knew this. And I knew that Leibniz probably got it using differentials. And I knew that Berkeley said that differentials was nonsense. Nonsense. And then I knew that a generation ago, differentials had been rehabilitated. No, not nonsense at all. Real stuff. Real stuff. And I have to confess to you that my knowledge of the rehabilitation of differentials didn't contribute one iota to my confidence in the validity of the derivative of x squared being 2x. I believe, number 9. I'll give a 9 and then 10 and then I'll switch a little bit. I have time. I believe that a certain result in computational hydrodynamics that was done on a supercomputer gives an accurate picture of a certain fluid flow. Now, I'm not going to write down any equations or explain this anyway. I have confidence in the group that produced the result. And I happen to know, since I was in this business at one point, when I was younger, that what they computed is of utility in the design of new airplanes. I have some confidence in that. On the other hand, there are conclusions reached the same way, more or less the same way, in which my level of confidence is lower. And for example, weather simulations or ozone or pollution or something like that, my confidence is lower in this sort of computation than in this one in pure, you might say, hydrodynamics. Now, let me finish this with one that sometimes engages people in a rather different way. I believe that every square matrix can be reduced to Jordan canonical form. I'll repeat that. I believe that every square matrix can be reduced to Jordan canonical form. Well, this happens to come close to my some of my everyday work in numerical methods. And I use this result frequently to prove theorems in numerical methods. And these theorems mesh fairly well with a certain complex of matrix material that I am used to and I am familiar with. I have only partial numerical verification of this because the Jordan form is notoriously unstable numerically. Every matrix that is non-diagonalizable is infinitely close to one that is diagonalizable. So you can understand the nature of the instabilities when you ask the question on a computer whether this matrix is diagonalizable or isn't diagonalizable. So I would say, well, I have partial verification of this numerically. Now, in view of this instability, I do not know exactly how to interpret this theorem if the data happens, if the numbers, the elements of my matrix happen to be physical data. Those are good to a couple of figures. I don't know. Now, I teach what this canonical form is. I express this canonical form in different ways. I know that there are many different proofs of this in different books, textbooks. I have never followed a proof. I find the proofs too long, excessively boring, or occasionally requiring far more abstract material than I am willing to cope with, or too much specialized language. I have never devised a proof of my own. I have never presented a proof in class. I have never told my students to look in such and such a book and they will find the proof and I will hold them responsible for it at the end of the semester. I'm quite comfortable with this. I'm very comfortable with that. All right. Let me say that I've approached this matter horizontally by giving a number of cases and telling you why I think that these statements happen to, why I accept them. Ooh. Let me pursue the matter a little bit vertically now and point out some of the components of evidence, not necessarily independent. I'm not certain that you could give a complete taxonomy of the varieties of evidence that people use for understanding, personal or otherwise. And I also suspect that quite apart from the so-called rigor that entered into mathematics, say around 1820, that what might have been considered evidence 400 years ago might not now be considered evidence. So the nature of evidence is itself a time-varying concept, I believe. Now, of these different points, I think that entire books could be written about them. And I think entire books have been. There's definition, there's naming, and there's axiomatics. I put them together. I don't mean that these are equivalent exactly, but I put them in one category. A square has 4 equal sides and 4 equal angles because that's what we say a square is. That kind of thing. Then, of course, there is proof in the standard mathematical sense. Proof, that was what the 2 graduate students were talking about. The name of the game in the classical mathematical sense, although that has changed. It's the feeling for what is a proper proof has changed over the past 200 years and is very likely going to change again, or is now in the process of changing. Now, these are components of, as I say, to remind you what I'm doing, is I'm making a taxonomy of evidence, types of evidence. There are computations by hand or by mechanical or by electronical devices, and computer proofs of all varieties. Chaos theory is full of what I call computer theorems. There are all kinds of things that come out of chaos theory. The pictures that are computed and then displayed contain all kinds of things which the eye sees and which would be exceedingly difficult to formalize in mathematical terms, what it is you're looking at, actually. But the running of the program constitutes evidence of the veracity of the thing. So there is visual evidence, visual proofs, and teachers often delight in obtaining, whenever they can, a visual or a graphical proof. And then there's other kinds of physical evidence. We don't like physical evidence. The volume of a cylinder. What is the volume of a cylinder? Well, Archimedes knew what the volume of a cylinder. Maybe Euclid knew what the volume of the cylinder is, but of course if you can, or of a sphere, or of a cone, let's say. But if you fill it up with water and then pour it into a graduate, you can get a experimental proof of what the formula says, or at least an approximate. Archimedes did not like that kind of thing. He separated that kind of proof from the strict mathematical proof, but we're always doing that sort of thing. Any analog experiment gives you some evidence that such and such is the case. Gauss is supposed to have triangulated the peaks of 3 mountains near Göttingen in an attempt to find out whether the angles of a triangle add up to 180 degrees. Then there's authority. Authority is evidence. If you want to know, ask Gauss. Gauss will tell you. Gauss, well, there's a modern Gauss. He will tell you. Or the textbook said. Textbook said on page 83, the textbook said authority. Or the table of integrals, which we used to use before we had Mathematica and so on. The table of integrals said so. Or the computer says so. These are evidence. Or the mathematical culture, the mathematical establishment says so. And I am reminded when I come to this piece of taxonomy, I'm reminded of something that Professor Heyman showed, the famous Roth theorem. Well, it was about 30 years ago. I found a way of applying the Roth theorem to a problem in numerical integration, approximate integration for functions that was singular. And I applied it to good use. Where had I heard of the Roth theorem? Well, it was in the mathematical reviews. That's where I first found it. It was stated in the mathematical reviews. I accepted it. Have I read the Roth theorem? No, I haven't read the proof. I accepted it on the basis of authority. And we do this all the time. Authority, what? It constitutes evidence. But what constitutes authority? Aha! The agreement of the community. Then there is analogy, proof by analogy, evidence from analogy, very strong. It's a way of formulating conjectures. There is formalism, evidence from formalism, evidence from symbol manipulation. Euler was great at that sort of thing. 1 minus 1 plus 1 minus 1 plus 1 minus 1. Divergent series. Nonsense? Not to Euler. Or not to Hardy, maybe. He wrote a book on it. And other people. So at one time it was nonsense. Then it goes back, it oscillates. Sense, nonsense, so on. And then there's aesthetics. This aesthetics can constitute an aspect of evidence. Something looks right, it feels right, it fits in with something else in a nice way. It completes something in a way that we find very pleasing, and so on. Aesthetics, experimentation, trial and error. And then irrational motives. What a devil are irrational motives? Well, my example for that, unexplainable confidence. Ramanujan or Ramanujan, I don't know how you pronounce the name. If you read his biography, had a goddess. This goddess told him something was true. I don't happen to have a goddess. He was lucky. Intuition, let's say, hunch, something like this. Then there are pseudo proofs, or quasi-proofs, statistical, probabilistic, zero knowledge proofs, where you don't have to tell anybody what the proof is, but you can convince them. I never understood this. You can convince them they had a proof, but you don't have to show them the proof. I don't know. Then there's common sense. And there's the Polya heuristic. Polya wrote 3 books on the Polya heuristic as pieces of evidence. And one form is like this. If A implies B and B is true, then it makes it more likely that A is true. You see, we wouldn't accept that in logic, but that's a good working principle. If A implies B and we know that B is true, then it's credible or more likely that A is true, you see. And then there is imagination. Imagination. Well, I'll let you, since I'm running out of time here, I'll let you supply your own examples of evidence via imagination. Well, I have other things. My God, it goes on and on. Insufficient reason, lack of contradiction. So far, there are theological reasons or evidence. I mean, God made the integers. You know, Kroneker's statement about that. And sometimes it's turned around. Hermann Weyl turned around and says mathematics is order, and order is evidence of the existence of God. But these are theoretical, these are theological things that come into mathematical discussions. But coming back to imagination, let me give you a quotation from George Bernard Shaw. And this will be found in Androcles and the Lion, his play Androcles and the Lion. Not in the play itself, but in the long introduction that he wrote to that. He said, people believe not necessarily because it's true, but because in some mysterious way it catches their imagination. So, having given you this very personal credo and confession, if you like, on the variety of reasons why I believe mathematical statements are true, I'll leave you to contemplate your own reasons. Thank you very much.